In this video, we are learning how to find the inverse of a matrix. In the previous videos, we saw how to perform operations on matrices, including addition, subtraction, multiplication. But we said there is no division of matrices. But this will replace the division operation. By finding these inverses, we're able to solve a matrix equation for a variable, for a variable vector. Okay, so first of all, the definition of the inverse of a matrix. If we have a square matrix, and a square matrix we're defining as the same number of rows as columns. If A is a square matrix of size n, right, we have this n by n rows, n columns, then the inverse of A will also be a square matrix of size n, such that when you multiply the matrix A times its inverse, you will get the identity matrix. Right, this is what we have demonstrated here, that A inverse times A, when you multiply it either on the left side or the right side, it's going to result in the identity matrix. In this case, when you multiply a matrix times its inverse, it does have that commutative property that we said that is not true in general for matrix multiplication. But when you're multiplying by the inverse, you do have that commutative property. All right, so if we were to look at an example, let's call the matrix A this 2 by 2 matrix 2, 5, 1, 3. Then we can say that its inverse, which we'll show how to find the inverse shortly. But the inverse for this matrix A is 3, -5, -1, 2, because when we multiply by A by A inverse, we get the identity matrix. Remember, the identity matrix is the diagonal of ones, everything else zeros. And also recall how to multiply. Remember, we are multiplying the first row times the first column, and we're adding we're multiplying each corresponding entry and adding them together. So we had this 2 times 3, which is 6, plus 5 times -1, which is -5. 6 plus -5 is 1. And then we would repeat that by multiplying the first row by the second column. And once you perform that multiplication, you would get 0 here, right? Because you get 2 times -5, which is -10, plus 5 times 2, which is +10. That cancels out, you get 0. Okay, if you repeat that throughout all of your rows and columns, you'll get this identity matrix. And since the product is the identity matrix, we say that 3, -5, -1, 2 is the inverse of that matrix A, 2, 5, 1, 3. Okay, but now the question is, how do we find the inverse, right? We know when it's the inverse, but how do we find the inverse if we're just given the matrix A? All right, so this is a general approach for finding the inverse of any size square matrix. Step 1, augment the matrix with the identity matrix. We talked about an augmented matrix, or augmented matrix in the previous sections in chapter 5. You had the coefficient matrix on the left side, and then you had the vertical bar on the right hand side was the right side of your equations. So same thing here. We've got the original matrix that's on the left side of the vertical bar. On the right side of the vertical bar, we'll have the identity matrix. We'll see how that works. But step 1, augment the matrix. Set that up. And then step 2, we're going to use the Gauss-Jordan elimination method to write the augmented matrix in row reduced form. Right? We want to get ones and zeros on that left-hand side of that vertical line. And the result, we'll have this I vertical line B, where I, that's the row reduced form part, and then on the right hand side of that vertical bar will be the inverse of the original matrix A. All right, let's see how this is set up. So we have the example to where we have a 3 by 3 square matrix, and we want to find the inverse of this matrix. So I will begin by augmenting this. So we're going to copy that matrix A. And then on the right-hand side of the vertical bar, we're going to have the identity matrix, this 3 by 3 identity matrix, where the ones are on the diagonal, everything else is zeros. Okay, now if you recall from section 5.2 and 5.3, we want to write this matrix in row-reduced form. In other words, we're trying to make this left-hand side right here to become the identity matrix. We're putting this in row-reduced form. Now we had 3 steps for this, right? We could interchange any 2 rows. We could multiply any row by a constant, or we can add a multiple of any row to another row. Those are the only 3 operations that we're allowed to do to this to get in row-reduced form. And this is where we work in columns, right? We start with the first column. We want to get our 1 first, and then get everything else to become zeros. Then we move to the next column and the next column until we're finished. All right, so on here, we want this first entry to become a 1. And we can do that by multiplying the first row by 1/2. So 1/2 times row 1 is 1, 1/2, 1/2, 1/2, 0, 0. Okay, now we want everything else in that first column to be 0. So we want that 3 to become a 0 and the 2 to become a 0. All right, do you remember how we were able to get those to be 0? We multiply the row that has the 1 in there already by the additive inverse of what we're trying to make become 0. So we're going to add to R2 -3 times R1, because if we added 3 plus a -3, that will give us 0 here. And we'll also subtract from row 3 a -2 times row 1. All right, but this row 1 stays the same. We're not doing anything to this first row. Okay, but we do need to change the second and third row. I'm going to come over here to the margin, see if we can work that out. So R2 -3 times R1. That's 3, 2, 1, 0, 1, 0. And -3 times R1, that is -3 times a -3/2. All of these are -3/2 here. 0, 0. We are adding these together. All right, that gives us the 0 in that first entry, which is what we wanted. 2 minus 3/2 is a positive 1/2. You may want to go through that calculation on your own just to convince yourself of that. 1 minus -3/2 is a -1/2, and 0 minus 3/2 is -3/2. And then 1 and 0, that is row 2. Okay, and then we'll do the same thing with the R3 minus 2R1. We're going to multiply by a -2 by row 1. So that's -2, -1, -1, -1, 0, 0. Adding those together. 2 plus a -2 is 0. 1 plus -1 is 0. Then a 1, -1, 0, and 1. All right, so first column is done. We have the 1 in the first entry, zeros everywhere else. So now moving to the second column, we want the second entry in the second column to be 1. We can do that by multiplying by 2. Everything else stays the same. And we'll have 0, 1, -1, -3, 2, and 0. And now we want everything else in column 2 to be 0. We already have a 0 in that last entry. We just need to get that 1/2 to become 0. And we can do that by taking R1 and adding a -1/2 times row 2. Everything else will be the same. So let's see what that's going to do to that first row. All right, R1 minus 1/2 times R2. So row 1 minus 1/2 times R2. So 0, -1/2 plus 1/2, +3/2, -1 and 0. When we add this together, we get 1, 0, 1, 2, -1, and 0. And again, you may want to verify those numbers on your own. So now column 2 is done. So the last column, column 3, we already have the 1 in place in the last entry of column 3. So we only lack getting everything else in the third column to be zeros. All right, I'm going to make some more space. Okay, so since I already have the 1 in place in the third column, I want everything else in that column to be zeros. I want this 1 and this -1 to become 0. And I can do that by taking my R1 and subtracting R3 from it, and then taking the R2 and adding R3 to it. All right, so my row 3 is already set in place. So let's see what my R1 and R2 are going to be. So R1 plus a -R3 that gives us 1, 0, 0, 3. That should be a +3 there. 3, -1, -1. And now R2 plus R3, 0, 1, -1, -3, 2, 0, plus 0, 0, 1, -1, 0, 1. That is 0, 1, 0, -4, 2, 1. And now the left-hand side of my augmented matrix is the identity matrix. That's row reduced form. So the right-hand side of my vertical line gives me the inverse. This will be A inverse. That will be the inverse of the matrix that I started with. Now you can verify this on your own. I'll let you do this on your own. Multiply matrix A times matrix A inverse and verify that the product results in the identity matrix.